Okay, we're going to go into the second part of section 2 of 9.2. And looking at these curves, we're going to actually use them, and they're going to model things like they would model, in this case, it could be population growth, or it could be interest in a bank account, and you're watching it grow. It could be, like I said, it could be radioactive decay. If you go up into the calculus sequence, we actually devise a differential equation that we solve, and it's going to measure radioactive decay, or it could be a population growth subject to a maximum population and stuff like that. You know what? They're all based upon exponentials. It's amazing. They have this quality about exponentials. Well, you'll see. Let's take a look here on I'm going to show you this application, and then I'll show you one more after that. So this particular one, perhaps you've seen this before, which would be cool. Compound interest, okay? Compound interest is a banking way of providing you money for your investment, okay, of some sort. And it goes according to this formula here. And I have all the characters lined up for your amusement, okay? So what it's saying is A is the amount in the account. Now we're talking about money, right? So how much is in the account as a function, of time? And that's written up here, amount currently in the account. Well, it's equal to P. What's P? The principal. And I spelled that wrong, I think, right there. It's principal. As in your buddy, the principal at school. That's money, okay? That's the principal, that's money invested, okay? So principal. And what happens is it multiplies with a quantity, and the quantity is 1 plus, okay? Up here, R is the interest rate, okay? And it's divided by N, and N is the number of years, number of times per year the interest is compounded. And then finally, time is in years. So here's a power, N times T. Now, in the Zoom meeting, we talked about it. We go, what happens in business is they go, hey, I'm going to give you 5% interest, let's say. So you go, I'm going to invest, say, $1,000, okay? And at the end of 1 year, let's say, compounded annually, okay, what they're going to do is they're going to tack on, if it's 5%, pretend, just goofing around, they're going to tack on 5% of what you put in there. So here's $1,000 times 0.05 as if you're tipping or something. And you end up with really 1,000 factored out 1.05 when you add those two together. And then you go another year, and you go another year. And it ends up being the next year would be 1,000 times 1.05 times another 1.05, and it gets squared, and it keeps going. But business people came up with a new thing. They said, how about instead of compounding at the end of the year, why don't we compound, I don't know, once a quarter, every 3 months, let's compound interest. Well, in that case, what they do is they give you $1,000, and then at the end of 1 quarter, they don't give you the full 5%. They give you the 5%, by the way, 0.05 is 5%, remember? Right? They give you 1/4 of the interest you're supposed to get times 1,000. And then what happens is at the end of the next quarter, you have this much, right? And then they add, okay, another quarter of 5%, and it just keeps going and going and going. So every quarter they give you a quarter of your money, and then another quarter of your percent, and then another quarter of your percent, until at the end you get the full 5% of interest, okay? And I've developed that formula. It's been a long time since I've taught business calculus, but the formula you end up with, let me see, oh yeah, it's this one, right there, okay? So A is equal to the principal, the money you invest, plus, and isn't it a weird formula? Look at the structure of it. It's 1 plus R divide by N. Remember that story? I took 0.05 divide by 4. 4 is the number of times quarterly that they're compounding per year, right? So that's the number of times they're compounding. So it starts to make a little bit of sense. This guy over here is you take it to the power n times t. N is the number of times per year you compound interest. T is the number of years you're going. So n times t really gives you the number of times that you are compounding throughout the entire time that you're collecting interest. So there's a method to this crazy madness. It's not just some magical thing. We're going to use it, though, right now. Okay, so look at Martha. This is actually out of your textbook, I believe. Martha takes $25,000 she invested it in a money market account for 10 years at a rate of 5.4%. So here's the fun. Determine how much this investment is worth if the interest is compounded quarterly, and then we'll go to monthly, and I think down here we go to daily just for fun to see what the differences are. Do you get more money? Yeah, it turns out you get a little bit more money, but not a lot more. Okay, so quarterly would be, you guys, all you have to do is you have to identify who's who. It says, how much is it worth? We're going to say A is equal to the principal, which is 25,000, parentheses 1 plus the interest rate, there it is. Why don't we call it 0.054? We're good with that. Quarterly, N is 4 times per year. So we divide by 4, take the power 4, and then finally, how many years? 10. 4 times 10. Okay? This is all this is calculation. Use your calculator and go to town with it. Okay? So that's what you would do in that case, is you would use the calculator. Okay. I don't have one with me and I don't have the numbers, so I'm going to let you do that. Monthly, okay? Monthly is, the amount is equal to, let's see here. Do you know what to do with that one? Why don't you try it? Okay, so I got myself a calculator. Let's do this thing. So when I take a calculator and I put this in, this is how I do it in case you're having trouble. It would be, I would type in 25,000, then I hit the times, or actually I don't even hit the times. If I've got my TI-30, I just put a parentheses, 1 plus 0. I actually type in 0.0544 or whatever it is. I type in 0.054, divide 4, close parentheses, up caret, and I might get lazy and go 4 times 10 is 40, and then I compute it. Let's see what you get. All right, so I'm doing it 25,000, parentheses 1 plus 0.054 divide 4, close, to the power, what did I say, 40? Okay. And we're at now, she started with 25,000. She's at, boy, that's pretty high, isn't it? She is at 42,745. So here we have 42,745. And I like to take it to the penny, and 47 cents. Okay. The next one, let's go for monthly. You compound it quarterly. What is it? What's the difference if we did it monthly? Well, monthly would say N is what? How many times per year is monthly? 12. That's right. So you go, this guy's going to be 25,000, right? And then 1 plus 0.054, because it's 5.4%, right? Divide by 4, and now, not 4 though, what is it really? 12. And over here, the power is 12 times 10. Let's put that guy in. So the numbers change a little. Okay, so if we plug that guy in, instead of dividing by 4, it's 12. And instead of the power being 40, what is it? It's 12 times 10 is 120. In that case, I get 42,848. So $42,848 and looks like 23, well, call it 24 cents. That's a little bit of an improvement. The money went up a little bit from 42.7 to 42.8. And the last one, daily, the amount would be equal to, once again, and it gets kind of redundant, right? Do you understand what we're doing here? It's 1 plus 0.054. This time, daily is what? N is 365 days in a year. So 365, but then 365 times 10 over here. So let's put that last one in. 25,000. This time you're dividing this guy by 365. 36. I have to insert, right? 5. And over here, the power is what? 3650. 3650 and 42,898. So this guy is equal to 42,898. Another 50 bucks, right? 0.46 and 46 cents. Well, there is a limit to this. Daily is quite often compounded daily. I've heard of old commercials that say that for banks if they want your money. Hey, man, we compound interest daily. Well, you're going to get a little bit more money when they do that. You know, it's just part of a machine that does it for you. I don't know if they do it anymore, but this is the kind of fun that you do with money. So if you compound like 4 times a year, you get 42.7, 48, 42.8, 42.8, and 50 extra dollars. Seems like there's no end to it, but there is. There is. And we'll learn that in a later section if we get there. Okay. Last application is problem number 38 from page 622. If 60 grams of carbon-14 are originally present in the fossil you find in an archaeological site, how much more will remain after 10,000 years? What? Okay. Example 6 on page 620 of the text tells us that the carbon-14 remaining in a fossil can be predicted by this model. It can't do anything without the model, so here it is. This is a different look. It's A is equal to A0, what's that, times 2 to the negative t divided by 5,600, like that. Ain't science great, right? Okay, so I'll have to fill you in a little bit. If you look at the example in the book, you'll know more about what's going on. Example 6 on page 620. Okay, it says there's 60 grams of carbon-14. That goes here. This is your principal, if you will. I'm going to tuck the 60 in there, and it goes, how much will remain after 10,000 years? That's a time. So think of this as there's a time variable, and then there's an amount variable. And that also rings true up here if you looked at this instead of just as a formula. It's a function of time once the rates and stuff are understood and known and fixed. But in this case, we're just basically going to say, plug in 0, you get an amount at the front end. In fact, if you plug in 0, what happens? Watch this. If t is equal to 0, then a is equal to a0 times 2 to the 0 power is equal to a0. And that's another reason why when you start the clock and you start with 60 grams, then your initial amount or your principal is 60. And that's why that guy goes in front. So when they tell us that the initial amount is 60 grams, we say, oh, I'm looking at a formula that looks like this. Okay, just grabbing it from the book and goofing around with it. And they have, like I said, you can watch them and watch their example as well. Okay, so now the question is, how much is left after 10,000 years? You know what I'm going to do? I'm going to go all the way out 10,000 years and figure out how many grams are left after that much time has elapsed. That means we're going to let t equal, doesn't that make sense? T is time, 10,000 years. Okay, what we're going to get here is a is 60 times 2 to the negative 10,000 divided by 5,600. All right, last one to get is a rotten egg. Let's grab our calculators and do this thing. In this case, what I would do to calculate it is I would go 60 and I would hit a times 2 up caret, and you know what? I use parentheses on this. I hit that little negative sign for numbers and I put dun, 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 divide, dun, dun, oh, 60, right? Okay. and see what you get. So let's do it. We're going to go 60 times 2 to the power, parentheses, negative 10, divided by 5,600, close, and get, wow, this guy dropped quite a bit. He's down to about 17.4. What's that stand for? Put it here. 17.4. What does that stand for? Grams of carbon 14. Grams of carbon 14. That's how much is left, which is interesting. 10,000 years later, you had 60, you're down to 17.4. This is one of the ways that scientists are, you've heard of carbon 14 dating. They're trying to figure out the age of archaeological specimens. And that's it. There you go. Have some fun with that homework. And I hope it goes well. See you at the next one.